We talked a little bit about friction earlier, but today I want to get into a little bit more detail on it and show you the two types of friction that we'll model and encounter in this class. There's a kind of friction called static friction, and that is friction that occurs between two surfaces at rest relative to each other. So let's imagine we have a box or a crate or whatever, and it's sitting at rest on this surface. There could be static friction there. The other kind of friction is called kinetic friction. That word kinetic implies motion. This is the kind of friction that occurs when you have two surfaces moving relative to each other. So here's the box with a surface, and we'll make it slide at some velocity v across this other surface. There could be kinetic friction there, a different kind of friction. Before we get into the equations and the model that we use for friction, let's look a little bit at why friction exists. That'll help us understand the model. Now, to do that, let me zoom in on this contact area between this top surface and this bottom surface. I want to zoom in close enough that we start to see the structure of the material. Even though this bottom surface looks smooth, if we take a magnifying glass and zoom in kind of close, we can see that it actually has some roughness to it. There's jigs and jags, and it's not perfectly smooth. The same thing applies to the bottom surface. It looks smooth, but it's actually not going to be. There's going to be jigs and jags, and it's not going to be perfectly smooth. This roughness, this surface roughness, is the main contributor to friction. Why do we have friction? Well, we have friction because this top surface, which is part of our box up there, has to slide across this bottom surface, and they're not smooth. So when this thing slides across there, it's going to have to bump up and over all these little jigs and jags, and that surface roughness is the largest contributor to friction. It's not a smooth slide. This is why lubrication decreases friction so much. If we took some kind of lubricant, like oil or water or whatever, and put it in between here, then it would fill all of these little crevices, and this top surface would slide across the bottom one much more easily. That's the main contributor to friction, just the surface roughness of the two surfaces that are sliding relative to each other. The same thing applies to static friction. If we remove this velocity so that it wasn't sliding but it was static relative to each other, to get the object to move, if I push on it and try to make it move, I'm going to have to break it free and start it bumping over these jigs and jags and that surface roughness. There's another factor that comes into play in static friction that tends to make static friction a little stronger than kinetic friction. There are some places on our object here where the object will kind of stick together. These 2 points are kind of close. They might stick together. Those 2 points might stick together. Those points might stick. And those points might stick. There's a bit of adhesion, a bit of weak chemical bonding that occurs. And so in addition to the surface roughness that we have to overcome, in the case of static friction, there tends to be more adhesion, more just sticking of one surface to another. And that can make static friction stronger than kinetic friction. So that's a bit about why friction exists. Let me back off of some of this so we have a cleaner picture, and then we'll write down the models that we use for each kind of friction. So let me back off of some of this. Get rid of those points and the oil that we poured in between those two surfaces. Okay, let's talk first about kinetic friction. What direction is it in, and what is its magnitude? The direction of the kinetic friction force is usually pretty easy to see. If the object is sliding this way, we know that kinetic friction is going to slow this object down and bring one surface to rest relative to the other surface. So there will be a friction force here directed back this way to the left. If the object is sliding to the right across this, the friction force on this top object is going to be to the left. Friction opposes the motion. Its job is to bring these two surfaces to rest relative to each other. So the two things we can say about the direction of kinetic friction. One is that it's parallel to the surface, and the other is that it opposes the motion. Now, how about the magnitude? What is the magnitude of the kinetic friction force? Well, that's complicated. Our model simplifies this to the product of two things. If we look back here, we can imagine that the harder these two surfaces are pressed into each other, so that these jigs and jags get embedded more into these jigs and jags, the harder they're pressed into each other, the more friction there should be. And that tells me that the kinetic friction force should be proportional to the normal force. The normal force tells me how hard one surface is being pushed into another. The larger that force is, the larger the friction force ought to be. So we model friction as being proportional to the normal force. But it depends on something else also. It clearly depends on how rough these two surfaces are. One way to decrease friction would be to get some sandpaper, sand this thing, make it smooth, and there would be less friction. Another way to decrease friction would be to get a different kind of material that was naturally smoother. If this box had a Teflon bottom, it would be smoother, and you would have less friction than if this was made of, say, wood. So how much friction there's going to be, what the magnitude of friction is going to be, not only depends on how hard the surfaces are pushed into each other, it also depends on what the two surfaces are, what their natural smoothness or roughness is. We lump all of that kind of material-specific thing into a constant that we call mu sub k, the coefficient of kinetic friction. Coefficient of kinetic friction. Typical values for the coefficient of kinetic friction go from 0 up to about 1. So mu sub k is always greater than or equal to 0. 0 means infinitely slippery, no friction. And it's less than about 1. 1 means it's really rough. A very rough surface is going to have a coefficient of friction approaching 1. For most objects, mu sub k, the coefficient of kinetic friction, lies somewhere in between there. And notice that it's a unitless constant here. Friction is a force, so it'll have units of newtons. The normal force also has units of newtons, so mu sub k is just a pure number. There's no units on it at all. It's a pure number that tells you basically how rough the two surfaces are. That's our model for kinetic friction, mu sub k times n. When you're working problems and dealing with friction, you almost always want to know what the normal force is first. How hard are the two surfaces being pressed into each other? Because until you know that, you can't figure out how strong the friction force is. So when I'm solving a Newton's second law problem involving friction, I always go for the normal force first. Until I know the normal force, I can't say how strong the friction force is going to be, because friction is proportional to n. All right, that's kinetic friction. Now, static friction is a little bit more complicated, and it's more complicated in this way. Kinetic friction, we say, always has the same magnitude, mu sub k times n. But static friction is definitely different. Suppose I push on this box with a pushing force of 1 Newton, and the box doesn't go anywhere. I know from Newton's second law that means that the friction force, I'm going to call it F sub s now, s for static, I know that the friction force is also going to have a magnitude of 1 Newton, because it's going to oppose my push, cancel it, and keep the object at rest. Now suppose I suddenly double my pushing force to 2 Newtons, and the box still doesn't go anywhere. Well, friction must be pushing with 2 Newtons. If I back off to half a Newton, friction is going to push with half a Newton. So static friction takes whatever value it needs to keep the object at rest. If you push sideways, static friction will push the opposite direction to keep the object at rest. But there's a maximum value. I can overcome friction. I can push hard enough that friction can't push back with the same magnitude so that I can break this thing free and move it so that I go into the kinetic case. Static friction takes any value it needs to up to a maximum. We write that like this. Static friction is less than or equal to some maximum value. What is the maximum value? How hard can static friction push? We model it very similar to this. There's a coefficient that lumps all the material-specific things, how rough, how smooth, whatever, into a coefficient of static friction. And we say it's proportional to the normal force also. The harder the two surfaces are being pushed together, the larger the maximum value of static friction. So this is the coefficient of static friction. Okay, so that's the maximum value. What the actual value is depends on what's happening. If you push with 1.5 newtons and the thing doesn't go anywhere, friction is going to push with 1.5 newtons. Let's get the direction of the static friction force. Like the kinetic friction force that was parallel to the surface, static friction is always parallel to the surface. But it can go left or right depending on what would happen if there wasn't any friction. If I'm pushing to the right, friction is going to go to the left. Static friction opposes what's called the impending motion. That's the motion that would happen if friction wasn't there. So if there's a net force to the right, absent friction, friction will oppose it and push to the left. If the net force is to the left, absent friction, then friction is going to be directed to the right. Static friction attempts to keep the object at rest on the surface. So the force of static friction is always parallel to the surface and opposite the impending motion. The impending motion is what would happen if there was no static friction. So those are our models for the two kinds of friction you'll encounter. Static friction is the more complicated one. You have to be careful here. It will take any value it needs to keep the object at rest up to a maximum. It doesn't always take this maximum value. It takes any value it needs to up to that maximum. Kinetic friction we model as being constant, mu sub k times n. When you're solving friction problems, the other tip I will give you, as I mentioned before, is to always find the normal force first. Until you know what the normal force is, you're not going to know much about the kinetic friction force. And until you know the normal force, you won't know how hard the static friction force can push. It might be pushing less hard than that, but you need the normal force to get the maximum value.